Welcome to this tutorial dedicated to the TIA Connect pattern library. We will discover how to generate complete, ready-to-use functional blocks in seconds for standard industrial components, motors, cylinders, sensors, safety, signaling. 40 patterns are available, 20 in SCL and 20 in LAD, all compliant with IEC 61131-3 conventions. Each pattern automatically creates the functional block, the DB instance, the input-output tags, and the storage folder. Let's see how it works. In any automation project, we find the same components: motors, cylinders, analog sensors, buttons, emergency stops. Each time, you have to create the functional block, define the interface with the correct inputs-outputs, write the control logic, create the tags, and create the DB instance. It is a repetitive task that takes time, on average 15 minutes per component. The pattern library solves this problem. It provides professional, ready-to-use templates that follow IEC 61131-3 naming conventions. The workflow is simple: browse the available patterns, examine the one you are interested in, instantiate it by providing a prefix and a folder name, and compile. The result: a functional block, a DB instance, tags, and a folder, all generated automatically in 10 seconds. 40 patterns are available, classified into 7 categories. Motors, direct start, frequency inverter, bidirectional, servo. Actuators, double-acting cylinder, single-acting, proportional valve. Sensors, analog, digital, IO-link. Safety emergency stop, safety door, safety zone, safety relay. Operator elements, push button, light tower. And functions, PID control. Each pattern exists in SCL and LAD versions, with strictly identical logic. 5 MCP tools are available for working with the library. For discovery tools, list_patterns to browse the catalog, search_patterns to search by keywords, get_pattern_details to examine a pattern in detail, and get_pattern_guide to consult the conventions. And the instantiation tool, instantiate_pattern, which generates the blocks, tags, and folders in the project. Let's move on to the practice. Let's move on to the demonstration. We have a TIA portal project already prepared with an S7-1500 CPU, opened in GUI mode to visualize the result directly. On the left, we see the details of the pattern we are going to instantiate: a direct start motor. The interface shows the inputs: iStart, iStop, iFeedback, iFault, iReset. And the outputs: ORun, ORunning, OFault, ORIADI. 3 logic networks will be generated: fault management, start-stop logic, and output mapping. We instantiate the motor_direct pattern. 3 parameters are enough. The prefix M01_, it will be applied to all created objects. The folder number 1000, the block will be stored in the 1000 motors folder. And the name of the tag table motors. In a few seconds, TIA Connect generates the semantic ML/XML, imports the functional block with its 3 logic networks, creates the DB instance, and creates the tags with their addresses. Everything is done. Let's compile the program. The compilation passes without error. The generated block is syntactically and structurally correct. In TIA Portal, we see the result. The 1000 motors folder has been created in the tree structure. Inside, our M01_FB motor direct functional block with its complete logic. Each network is commented, each variable is named according to IEC conventions. The motors tag table contains the 5 tags with their addresses. And the DB instance is linked to the functional block. Everything that would have taken 10 to 15 minutes to do manually was generated in a few seconds. Let's add a second component to our project: a double-acting pneumatic cylinder. On the slide, we see the pattern interface, output command, return command, position feedback via 2 limit switches, and status outputs. The block also handles timeout detection and fault management. We instantiate the cylinder with the prefix CYL01 in the 2000 actuators folder and the actuators tag table. The storage convention separates motors in the 1000 series and actuators in the 2000 series. This structures the program professionally. In a few seconds, the block, its DB instance, and its tags are created. Let's recompile. Still no errors. 2 patterns instantiated, 2 complete components, and we haven't written a single line of code. To complete our machine, let's add an emergency stop. The emergency_stop pattern manages the emergency stop button with mandatory acknowledgement. As long as the operator has not acknowledged, the machine cannot restart, even if the button is released. This behavior complies with safety standards. The prefix ES01 and the 200 safety folder, safety blocks are stored in the 200 series. After instantiation and compilation, we have a complete safety block with interlocking logic. Let's look at our project tree after 3 instantiations. We have 3 well-organized folders: 200 safety, 1000 motors, 2000 actuators. In each folder, the functional block and its DB instance. 3 tag tables: safety, motors, actuators, each containing the tags of the corresponding component. In less than 2 minutes, we have built the basic structure of a professional automation program. In TIA Portal, the tree structure is clean and organized. Each folder corresponds to a functional category. The blocks are complete with networks commented in detail. An automation engineer taking over the project immediately understands the logic. The tag tables are separated by function. The DB instances are linked to their respective functional blocks. This is exactly the quality of structuring expected from a professional project. All that remains is to call these blocks in OB1 and wire the inputs/outputs. The pattern library is particularly powerful when driven by an AI agent via MCP. The automation engineer gives an instruction in natural language, for example, add a second M02 frequency inverter motor. The AI agent searches for the right pattern, examines its definition to understand what it will create, instantiates it with the correct parameters, and compiles everything. The automation engineer only has to validate the result. The patterns respect IEC 61131-3 conventions. Functional blocks are prefixed with FB, DB instances are prefixed with DB, inputs start with I, outputs with O, static variables with stat, and constants are in uppercase. The storage convention by numbered folders organizes the program logically: 200 for safety, 500 for sensors, 1000 for motors, 2000 for actuators. These conventions are based on the library standard, widely used in the industry. A few best practices to get the most out of the pattern library. First, choose consistent prefixes: M01 for the first motor, M02 for the second, CYL01 for the first cylinder. Second, respect the folder numbering convention. Third, always examine a pattern with get_pattern_details before instantiating it. Fourth, compile after each instantiation to validate that everything is correct. And fifth, SCL and LAD patterns are functionally identical. The choice depends on the team's preference or the client's standards. Let's recap what we have just discovered. The TIA Connect pattern library provides 40 professional templates for the most common industrial components: motors, actuators, sensors, safety, signaling, regulation. Each pattern automatically generates the functional block with its complete logic, the DB instance, the input-output tags, and the storage folder. All while respecting IEC 61131-3 conventions and automation library structuring. In a few minutes, you can build the basic structure of a complete automation program, where it would have taken hours of manual work. The patterns are available in SCL and LAD, with strictly identical logic. The library is accessible via the integrated Copilot, via MCP for external AI agents, and via the API. Thank you for following this tutorial. See you soon on TIA Connect.